Hi, my name is Aparna Elangovan. I'm a solutions architect here at Amazon Web Services, specializing in machine learning. And we are so glad to have you joining us today for this series of webinars on ML services offered by AWS. This particular session, Open Source ML Frameworks on Amazon SageMaker, featuring TensorFlow, PyTorch, MXNet, Keras, and Gluon, will show you how to use these frameworks on Amazon SageMaker. This is a technical session and assumes that you worked with at least one deep learning framework before. Amazon SageMaker provides every developer and data scientist with the ability to build, train, and deploy machine learning models quickly. Amazon SageMaker is a fully managed service that covers the entire machine learning workflow to label and prepare your data, choose an algorithm, train the algorithm, tune and optimize it for deployment, and make predictions. SageMaker has built-in support for machine learning frameworks TensorFlow, PyTorch, Chainer, MXNet, and scikit-learn. TensorFlow is a leading choice among many frameworks for deep learning workloads, and a recent study found that 88% of TensorFlow production workloads running in the cloud are actually running on AWS. When you choose to use Amazon SageMaker, your machine learning experiment is automatically tracked, making it easier to repeat your experiment. As an example, attempts to improve your model can take weeks, and sometimes your first model might be the best one. So if you want to replicate a run as of a certain point in time, you would have to figure out exactly which settings were used. With SageMaker, all the hyperparameters, code, and data are automatically tracked for you, making it much easier to replicate your experiment. SageMaker also makes it very easy, as simple as one click, to productionize your model into an API available over HTTP. Now, let's look at how all this happens. We can look at SageMaker as having two different phases, like the two machine learning phases, the training phase and the inference phase. During the training phase, you provide your source code, your data in Amazon's simple storage service, also called S3, a Docker image, either built-in or you can bring your own, and finally, the type of EC2 instance you want to use for your training, such as a GPU or a CPU-based instance. Generally speaking, it is better to have your training data in S3 as opposed to the training job directly connecting to a database. This is because if you want your machine learning training job to be repeatable, your training data should not change. With S3, you can put IAM rules and policies in place so that the data is immutable. When you launch an Amazon SageMaker training job, SageMaker automatically provisions the EC2 instances for you and shuts them down when the training completes. So you only pay for when your training job runs, optimizing cost. It then pulls the Docker image that you specify, downloads your code and data from S3 automatically. It then executes the training job and copies the results and models back from the container host to S3. One cool thing here is halfway through, say you cancel your job, SageMaker will automatically copy all the artifacts created so far into S3. This is a useful functionality, especially as part of training. If you've been snapshotting the best model so far, you don't have to worry about losing the best model if you choose to stop the training job halfway through. It also captures all the log and print statements that you write to the console in Amazon CloudWatch. This allows you to go back in time and look at past history of how the job ran. It also captures the infrastructure metrics such as CPU, GPU, memory, and disk utilization, which become helpful when you want to optimize the time it takes for your training. It can also track the model performance metric, such as mean squared error or any custom metric you choose. Next, let's look at the inference phase. During this phase, you provide the S3 location of where the model-related artifacts are stored, a Docker image either built in or your own, and the type of instance you want to run the inference on. SageMaker automatically launches the instance and runs the Docker container. It then downloads the model from S3, and with a single line of code or single click, you have your inference endpoint ready. This endpoint can automatically scale based on an auto-scaling policy that you specify. For example, say you start off with a single instance for inference, and then you apply a policy that says if the number of requests per second is more than a threshold, then increase the number of saving instances to 2. The same applies when the number of requests go down and the scaling policy to scale down kicks in, and the number of instances can be reduced to 1. This sort of auto-scaling policy optimizes cost, performance, reliability of your machine learning application. Just like the training phase, all the logs and metrics are automatically captured in CloudWatch. This allows you to look at information such as how your model was used and how frequently it was used to produce the results and model latency. Now, let's look at a more concrete example on how to use TensorFlow and Keras with Python 3 on SageMaker. This example here is a typical ML code base with a couple of Python files and the dependencies specified in a requirements file. Now, let's look at the entry file in this example called the main_train.py. The code snippet shows you a typical parser in Python where you require some parameters such as the training data location, the number of epochs to run your training job. Now, in order to submit this code as part of SageMaker, here's a sample of what the job submit code would look like. First, when you use TensorFlow on SageMaker, you tell it where the source code is located and what the main entry file is. Your source code can be located either in S3 or the local file system. The entry point file is located relative to the source directory. Now, SageMaker knows where to find your code and what the entry is. Next, you have to tell SageMaker where the training and validation datasets are located. These are called channels in SageMaker. And this is how you would specify that. When you submit your training job, you pass in a dictionary that maps keys to S3 locations. Within your code, you reference the data downloaded using the environment variable sm_channel_keyname you used. In this example here, your code would find the training data directory from the environment variable pointed to by sm_channel_train, and the suffix train matches the key name in the submit job. You can call this by any name, say ABC, then the dictionary key name would be ABC, and you would refer to it by using the environment variable sm_channel_abc. One thing to note here is that the data is automatically downloaded for you from S3 location that you specify and is placed in the local file system in the path pointed to by the environment variable prefixed with sm_channel_. This means you can use your usual file operations to read and write data without having S3 specific code, and this gives you the flexibility to run your training on either your laptop or on AWS. Next, you want to specify any hyperparameters for your training job, such as the batch size or the number of epochs. And this is how you do it. You pass them as hyperparameters, and the names of the arguments you have in your code match the name of the hyperparameter dictionary key. For example, the name epochs here match the name epochs here. Next, you save your model artifacts in your local file system so that when the training job completes, SageMaker automatically uploads them to S3. And this is how you do it. You save your model artifacts in the file system pointed to by the environment variable sm_model_dir, and in your code to submit your job, you specify the S3 path to upload your artifacts to. Finally, you tell SageMaker what type of instance to use for your training job. In this example here, we are using a ml.c4.extra-large instance type. And this is it. SageMaker will now launch an ML_c4 extra-large instance, pull a TensorFlow Docker container, download the code and data pointed by the S3 locations you specify, execute your code, capture all the logs and metrics, and then upload all the output artifacts to S3, and then eventually shut down the training instance so you're only charged for the duration of your job. Next, let's look at how to track your model-specific metric. When you run your training jobs, you want to know how your model performs on a validation set. With SageMaker, you can automatically track a model metric such as mean squared error and visualize it on a dashboard. Here's how you do it. This is a typical Keras code that constructs a model and evaluates it. So for SageMaker to track the performance of your model, you simply print the results in a specific format. In this example here, I'm printing the mean squared error, the mean absolute error, and mean absolute percentage error. Using the convention ## space followed by validation _metric _ followed by the metric name and then the score. As part of my training job submission script, I specify the regular expression that will extract this expression from the log files. And finally, you specify the TensorFlow versions and the Python version you want to use as shown here. In this example, we are using Python 3 with TensorFlow 1.11, and these versions are used to launch the right SageMaker containers to execute your training job. Now, let's switch to a demo and see how this all fits together. This demo is to predict the age of abalone, a type of shellfish, based on its physical characteristics such as height, weight, and diameter. I'm going to walk through the components of a typical ML code base. You have a main entry file that parses the arguments and starts the training. This code shows a general training process where you define the deep learning network, the optimization criteria, the code to load the training data, fit the model against the training set, evaluate it against a validation set, and print the results. The metrics printed are mean absolute error, mean absolute percentage error, and mean squared error. The format in which the metrics are printed must be uniquely extractable via a regular expression. You then specify this regular expression when you submit the job as shown on the previous slides. And finally, you save the model. You save the model in a TensorFlow format as opposed to the native Keras format because you can take advantage of the built-in TensorFlow model to save your model. Another thing to note here is where the model is saved. The variable model_snapshot dir is an argument passed to the train function. If you look at where that's coming from, it comes from the input parser and by default points to the directory sm_model_dir. The rest of the code block shows a typical argument parser. In Python, to parse the input argument, you would pass through a command line and start the training process. Next, you have the model exporter that exports a Keras model to a TensorFlow model. This is pretty much boilerplate code, and you would find more details on either Keras or TensorFlow documentation or on Stack Overflow. You also have a requirements file used to specify the dependencies so that your code can be consistent no matter where you run. And finally, you have a setup.py that is required so that your code is marked as a package. Let's look at the argument parsing step in detail. The code block here parses the input argument and uses default values to load the data from directories pointed by SageMaker environment variables. This is a neat way of having the option to provide alternative inputs and making it SageMaker compatible. Now, let's look at how to deploy this code as part of SageMaker. You can deploy your code on SageMaker using SageMaker SDK in Python or as part of a CI/CD pipeline. For the purpose of a demo, I'm going to use a Jupyter notebook to submit training jobs and then deploy an inference endpoint. It is a fairly straightforward process to create a notebook instance on SageMaker as shown here. It does take a few minutes to create a notebook, and I'm going to use Jupyter Labs for this demo. Jupyter Labs provide a nice, convenient way to browse your files and code as opposed to a notebook on its own. I'm going to use a terminal to pull my code from Git. If you want any files to be persisted between notebook restarts, you want to make sure they're placed in the home/SageMaker directory. I have now cloned my code onto a notebook instance. Let's have a look at the notebook. When you launch a notebook for the first time, you would have to select a kernel. Because I'm demonstrating code that requires TensorFlow and Python 3, I select the TensorFlow Python 3 kernel. In Jupyter Notebooks, kernel is a process that interprets and executes your code. The conda_TensorFlow_p36 kernel comes with Python 3, TensorFlow, and SageMaker libraries already installed. You can create your own kernel, in which case you would have to reinstall the right Python version and any other dependencies your code needs to run. First, you set up the environment. The role here is an important one. This is the one that gives SageMaker job permission to access resources such as your S3 bucket where your data is located. Let's quickly explore the datasets. The features used are the age of abalone, the diameter, height, and weight, etc. The label is the age, which is what we want to predict. Next, I'm going to upload my code. Next, I'm going to upload my data used for training and validation to S3. This is for a demo. Ideally, in a production scenario, you would have a data lake with all the training data set up for ML in S3. The dataset has 3 files for train, validation, and test. I'm listing the contents of source directory just to show you the code files that I showed you on the PyCharm IDE. This is how you submit the training job, and the code sample is exactly the same as the one we saw on the slides before. These are Python statements and function calls, so you can integrate them into your CI/CD pipeline without having to use a notebook. Let's start training. Now, if you go back to the SageMaker console, you can see that the job is starting. You can see that it has captured the job status, the container or the algorithm in this case, which is TensorFlow, the input channel and its corresponding S3 location, the validation channels, the metric to capture model performance, hyperparameters required to start the job, such as the batch size, let's see how the job is looking through the Jupyter Notebook, and looks like it's completed successfully. The training job has quite a lot of useful logging information. For instance, it has installed the dependencies in the requirements file. It shows how the inputs were used to start your main entry file. You can also see the print statements of the validation scores have been logged. Let's go back to the SageMaker console and see what has been tracked. The job status is recorded as completed, and most other attributes of the training job remain the same. Let's look at how some of the performance metrics are tracked. It shows the infrastructure performance, visualizing your instance performance, such as CPU and memory utilization. You also get to see your model performance and metrics displayed. You can see that your model metric you printed with your code, such as the mean absolute error, mean squared error, and mean absolute percentage error, is displayed in a graph. That's pretty cool. If you look at the model output, SageMaker has automatically gzipped the artifacts you saved in the location pointed to by the environment variable sm_model_dir to S3. Now let's look at how to turn this model into an API. This is just one line here that says deploy and passes the instance count and the type as an argument. I've used a single T2 medium instance to host my endpoint. That's how easy it is to set up your model and make it available over a HTTP endpoint as an API. Now let's invoke it with some sample data. The code here simply loads the test CSV into a TensorFlow dataset. Let's print the features of abalone we want to predict the age for. In this demo, I also have the actual ages, so let's print those as well to compare them with the predicted ages. The code here invokes the API over HTTP, and here are the predictions. Let's go back to the console and see the endpoint. The HTTP URL here is a URL your clients would use to invoke the API. This endpoint is by default secured using IAM policies, so you have to give your clients explicit IAM permissions to invoke it. You can see that it has captured the infrastructure-related metrics. The endpoint runtime settings here are related to auto-scaling policies. Because this is a sample code, I have not applied auto-scaling, so the initial count of 1 is the same as the desired count. With SageMaker Endpoint, you can do A/B testing, where you route some percentage of the traffic to one model and rest to the other. In this demo here, there's just one version of the model, and hence all traffic is routed to the same model. This is the end of the demo, and let's switch back to the slides. In this section, let's look at how to use PyTorch with SageMaker. The method to submit training job is very similar to TensorFlow with one minor change. Instead of specifying TensorFlow, you specify PyTorch to submit the job. Here you've specified PyTorch, and similar to TensorFlow, you specify the source code location and the entry point file. Just like in TensorFlow, you specify the training data location in S3 and use the key name as the suffix to the environment variable sm_channel_ to load your training data. Next, you specify the hyperparameters. Next, you specify the model path. And finally, you specify the instance type. You can see this is very similar to the TensorFlow job that you previously saw. Before I get into the details of how to implement inference on PyTorch, I want to go through a general inference phase. For the TensorFlow demo, we implicitly use the TensorFlow model server when we call the deploy command. For ML frameworks that do not have a model server, this is a general SageMaker inference flow that shows you how to customize this process. First, the client submits a HTTP request containing the data you want to run the predictions for, along with the authorization header token required to invoke the endpoint. The HTTP request also contains the content type to specify what the format of the payload is. The payload can be a JSON file, as shown here. It can be a CSV formatted one, or any other format you choose. When the request reaches the SageMaker endpoint, you can write custom code to parse the request based on the request content type to produce a Python object. And the custom input function is passed the request body and the content type to produce the results. Depending on the framework, the model object can also be one of the inputs to this function. The model_fn is executed once at the start to load the persisted model from disk and deserialize it to produce a Python object required to run predictions. Once the input is parsed into a Python object, the input object is passed to a predict function to run inference. The resulting prediction object is then passed to an output function that serializes the Python object depending on the response content, based on the accept header in the request. Please note that the exact details depend on the framework and the version, so do check the SageMaker documentation. You looked at the training phase for PyTorch. Unlike TensorFlow model server, there are no built-in model servers for PyTorch. So you have to define a model function, model_fn, that loads and deserializes the model from the file system. The model load function is going to be boilerplate code in most cases. Here's the example. Make sure the signature of the function matches the one specified here, including the return type. I also want to show you another nice little trick. You can deploy your code in either an instance that only has a CPU or an instance that has GPUs. So you want your code to make use of either the CPU or GPU if that is available. This code here shows a PyTorch way to check if GPU is available, then use the GPU, else use the CPU. Next, let's look at some more extensions that SageMaker offers. In this section here, we are going to look at MXNet on SageMaker. By now, you should be very familiar with the way that you can submit SageMaker training jobs. MXNet on SageMaker is no different. You just change the name onto MXNet to launch MXNet on SageMaker, and everything else follows the same pattern we went through for TensorFlow and PyTorch. MXNet comes with a model server, so you don't have to write code to load the model. If your only artifact required for inference is an object of type MXNet nn.module. But if you're working in natural language processing, you usually have additional artifacts, such as the vocabulary, that needs to be loaded along with that model. In that case, you would have to write custom code to load the model. This example here shows you how to load a glue-on model, and as always, the function signature needs to match so that your custom code is executed when SageMaker calls the function model_fn. This is a slightly advanced functionality to show code examples for the general SageMaker influence flow I went through a couple of slides ago. If you use standard formats like JSON in your HTTP request, you would normally not have to customize your input requests or output responses. But in this example here, I'm using a binary-like format, a pickled version of ND-array, as my HTTP request content. So this custom input function transforms the binary format into a Python MXNet ND-array object. You can do the same for the output formats as well. The function signature should match the ones required for a specific version of MXNet on SageMaker. In this session, we looked at how to submit training jobs on SageMaker using Keras, TensorFlow, MXNet, and PyTorch. We also looked at how to deploy inference endpoints on those frameworks. In summary, Amazon SageMaker offers an alternative to building your own machine learning pipeline and removes the complexity for both developers and data scientists. It allows your code to be portable and yet take full advantage of Amazon SageMaker functionality, such as experiment tracking, hyperparameter tuning, and allows you to very quickly productionize your model by deploying an endpoint API and make it optimized for cost, performance, reliability, and security. If you have any questions, please ask the experts, and you can learn more about machine learning on aws.amazon.com/machine-learning. You can also access training resources on www.aws.training for machine learning. Thank you again for attending, and we really appreciate your feedback so that we can better understand the topics and services you would like to know more about. So please do take the time to fill out our survey and let us know what you think. Hope you enjoyed this session and it helps you migrate your ML solutions running on laptops to a production quality ML pipeline on SageMaker. Happy coding, and let's go build.